Have you ever just stopped and wondered what the super abstract world of pure math really has to do with the phone in your pocket or the computer you're looking at right now? Well, it turns out there is this deep, incredible connection, and it's all powered by one of the oldest ideas in all of mathematics: prime numbers.
Okay, so let's just dive right in. What on earth do prime numbers have to do with all the zeros and ones that make up our digital world? Now that question, it seems pretty simple on the surface, but it actually holds the secret to how everything we build with computers is even possible. And the journey starts, well, not with electronics, but with the search for a perfect number system.
So to find that answer, we first have to imagine sort of an ideal mathematical world. A place where all the rules of arithmetic, adding, subtracting, multiplying, dividing, just work flawlessly every single time, with no weird exceptions. In mathematics, this perfect little world has a name. It's called a field.
So what is a field? Well, it's basically a set of numbers where everything just works. You can add, you can subtract, you can multiply, and this is the really crucial part, you can always divide by any non-zero number. Now, that ability to divide depends on every non-zero number having something called a multiplicative inverse. You probably know it better as its reciprocal, like how the inverse of 2 is 1/2.
Okay, check this out. This slide really shows why the numbers we use every day, the integers, -2, -1, 0, 1, 2, and so on, why they aren't perfect. Let's just take the number 3, for example. What's its multiplicative inverse? It's 1/3. But is 1/3 an integer? Nope. This one little flaw means the entire set of integers is not a field. Mathematically speaking, it's kind of broken. So, if the integers are broken, can we actually fix them? Well, it turns out we can, and we do it with this really clever mathematical trick called modular arithmetic. I want you to think of it like this. We're taking the infinite number line that stretches out forever, and we're literally wrapping it into a finite circle.
Let's try this fix with the number 5. So now we're only dealing with the remainders you can get when you divide by 5. That's just 0, 1, 2, 3, and 4. Now look at this multiplication table. Do you see it? Every single row has a 1 in it. That means every single number now has a multiplicative inverse. For example, look at 2 times 3. That's 6. But in mod 5, 6 is just 1. So 2 and 3 are inverses of each other. It works perfectly. We've just created a field.
This is awesome. I mean, it feels like we've cracked it, but hold on. This leads to the really big question. Did we just find a universal fix for numbers? Can we just pick any number we want, do this whole mod thing, and create a perfect field every single time?
All right, let's put our idea to the test. We're just going to move to the very next number, 6, and see if this brilliant idea holds up. We're going to build the tables for the integers modulo 6, or R6, which is just the numbers 0, 1, 2, 3, 4, and 5.
So first up, let's look at addition. And as you can see from this table, everything looks great. It's all working. You take 4 plus 3, you get 7, which in our mod 6 world is just 1. 1 is in our set, so addition is closed. It all works just fine. Okay, so far so good.
But then we try multiplication, and oh boy, it is a complete and utter mess. All of a sudden we have these rogue zeros just appearing out of nowhere. Look, 2 times 3 is 6, which is 0 in this system. And check out the rows for 2, 3, and 4. There's no 1 in any of them. That means they've completely lost their multiplicative inverses.
So what's the takeaway here? The crucial point is that 3 different numbers in our set, 2, 3, and 4, suddenly have no inverse. There's nothing you can multiply them by to get back to 1. This means our system is totally broken again. R6 is not a field.
So why? Why did our fix work perfectly for the number 5, but then fail so spectacularly for 6? I mean, they're right next to each other. Well, this isn't random. There is a beautiful hidden pattern at work here, and it is the key to our whole question.
And right here, this slide just brilliantly illustrates the problem. The numbers that failed, 2, 3, and 4, all share a common factor with our modulus, 6. The modulus 6 can be factored into 2 times 3, and those are the very factors that snuck in and broke our system. But 5? Well, 5 is a prime number. It has no factors other than 1 in itself, and that is the critical difference.
And this right here, this reveals the fundamental rule. This whole amazing system of modular arithmetic only creates a perfect self-contained mathematical world, a field, if and only if the number we use for our modulus is a prime number.
Okay, so this is huge. We've just discovered that prime numbers create these perfect little mathematical toolkits called finite fields.
But, a field is just a set of numbers. To build something truly powerful, something like a computer, we need more structure. So the question becomes, what can we build on top of these perfect little fields?
Well, we can use a field as the foundation to build something much bigger, a vector space. You can think of vectors as lists of numbers, kind of like coordinates on a map. The vector space is the whole map itself, and the field is what provides all the numbers we're allowed to use for those coordinates.
And building a vector is actually way more intuitive than it sounds. You just pick your field, any field will do, then you decide how many dimensions or components you want your vector to have. You make that many copies of the field, and then you just pick one number from each copy and arrange them in a nice ordered list. That's it. That's your vector.
Now, when we start adding vectors, it's really important to understand that we're actually using two different kinds of addition at the same time. You see here that big bold plus sign on the left? That means vector addition. It's our new rule for combining entire lists. But inside the brackets, those smaller plus signs are just the normal field addition that we've been using all along, just applied to each matching part of the vectors. All right, so we've gone from integers to fields, and now to vector spaces. I know, it's been a pretty abstract journey, but now it is time to connect all of this back to our original question and see why this pure math is literally the foundation for every computer on the planet. Let's apply our prime number rule. What's the smallest prime number there is? It's 2. So what's the smallest, simplest possible field we can create? Well, it's the integers modulo 2. And what are the only elements in that set? Just the remainders you can get when you divide by 2, 0 and 1. Does that sound familiar?
And here it is. This is the giant leap. Just look at what happens when you do arithmetic in this tiny little field of 0 and 1. Addition in R2 is mathematically identical to the XOR logic gate in a computer. And multiplication? It's identical to the AND gate. This is absolutely not a coincidence. It is a fundamental property of this prime field.
So this is it. This is the real reason our computers use zeros and ones. It's not just some convenient choice for representing on and off with high and low voltages. It's because the set containing just 0, 1 forms the simplest possible, mathematically perfect, and internally consistent field. It is the absolute bedrock on which all of digital logic is built.
So from now on, whenever you see a string of zeros and ones, you'll know it's not just a bunch of simple switches. It is the language of a perfect, tiny mathematical world, a world built on the elegant and ancient power of prime numbers. And it really makes you wonder, doesn't it? What other secrets from the world of pure math are hiding just beneath the surface of the technology we use every single day?